Namaskaram. The first thing that we have to do whenever we learn a new language like mathematics is get a grip on the basic tools, the basic syntax of the language, which then can be used at all levels. So what we'll see here is once you get a grip on the basic ideas behind the subject, you will start to see that the same tools, the same ideas will basically be applied at all deeper levels of the subject. So it's very important to get a handle on the basic ideas. So let's try to do that over here. Now, what we have here is a simple real life example. I have a car which is basically driving on this straight road. Very simple example. Now the car is already in motion. Let's think of it like that. And the situation is very simple. What we have here is this car is going in a very steady, very smooth way. It's not becoming faster and it's not becoming slower. It's just kind of cruise controlling its way down the road. And what are the numbers that we have over here? This car is going in such a way such that with every passing second, the amount of distance the car covers on this straight road is exactly 5 meters. So it's not becoming faster, not becoming slower. It's just cruising. How is it cruising? With every passing second, it covers 5 meters, 5 meters, 5 meters, 5 meters, and so on. It can keep going. Now, how do we measure all these quantities? We measure all the quantities from the start position. In any experiment, it's always important to know what are the conditions at the start of the experiment. We'll see this later as something called initial conditions. Initial conditions are what are the conditions initially at the start of the experiment. So we've had the start point marked here. So if I want to measure passing time, I measure it as we get it from the start. So imagine somebody standing here with a stopwatch, right? When you measure somebody's timing in a 100-meter race or something like that, right? You stand at the start and you have your stopwatch and it's at 0 seconds. So the moment the car starts moving, as it moves, then we start our stopwatch and we measure how much time it has taken to move some distance from here. The start is always here. Another way to think about it is the reference position from which we measure everything. So time is measured from here. Similarly, the distance traveled by the car along the road is measured from this start position. So we again start from here. So our time starts from here, 0 seconds. The distance also starts from here. This is our starting point for distance, 0 meters. So after 1 second, as you can see, the car starts from point A. After 1 second, 5 meters reaches point B. 1 second has passed. It is now 5 meters away from the start. After another second, car reaches point C. Another second has passed. Total time from the start now has passed is 2 seconds. And the total distance therefore is 5 plus 5. It's at 10 meters away from the start. You can keep going. After 3 seconds, 15 meters. After 4 seconds, 20 meters, and after 5 seconds, 25 meters. And as you can see by the arrows at the end, this can continue until the end of time, until the driver gets tired. I don't know, right? So that's basically the story, right? So if you want to tell anyone the story, you basically tell them all of this. Okay, there's this car, it starts from here, with every passing second it travels 5 meters, and we can measure the distance accordingly, and this story goes on. Perfectly right. This is all okay. This is where mathematics comes in. Now, this is a very long story to tell, right? Too many things, too many long sentences. The main aim of mathematics is to take a real life situation and take a long story, make it short, make it succinct. It's like a summary exercise in many ways. That's the first point. And the second point, not only does mathematics help making a story which is long, succinct and short, it also helps it make it very clear with no ambiguity, no doubt about what exactly is happening. So how does mathematics do that? Well, what we have here is the same story written in the language of mathematics. Let's look at how we write that. This whole story can be written in this way. The distance that the car has traveled from the start, can be calculated by distance from the start will be got by doing a simple calculation. I first find out how much distance the car is traveling per second. Another way of saying it is for every unit of time, in this case a second, in 1 second how much distance the car is traveling, distance travel per second. Once I know that, then all I have to do is multiply that with the total amount of time that has elapsed from the start. If it's traveled 5 meters for every second, and if I want to find out where the car is after 5 seconds, what do? 5 meters for the first second, 5 meters for the second second, the third second, the fourth second, and the fifth second. So basically what we're doing is we're adding this value, distance travel per second, how many ever times we want based on how much time we are interested in checking for, right? If it's 5 seconds, we add this 5 times. A simple way of doing adding something 5 times is simply multiplying by 5. Multiplication is a short version of addition, that's all. So that's basically it. If I want to know the distance from the start, find out how much distance is traveled in 1 second or in 1 unit time, multiply that with the total time that you are interested in, and you will get the answer. And we can see that over here. If I want a total time of 5 seconds from the start, I know it's traveling 5 meters in 1 second, 5 meters in 1 second into the total time that you want, which is 5 seconds. 5 into 5 will give you 25 meter from the start. This basic calculation is something that we all do even when we go to a stationery shop, for example. You go into a stationery shop and you want to buy pens. The first thing the shopkeeper tells you, hey man, a single pen, one pen costs 10 rupees. So 10 rupees per pen. If the per pen cost is 10 rupees, and if you want to buy say 10 pens, what do? 10 rupees per pen into the number of pens you want to buy, 10 in this case, 10 into 10, you need to spend a total of 1000 rupees. That's all. The same logic is applied here. This is very useful for us because now it tells us this whole long story in a very simple, short, and also very clear way, no doubt. We can now rearrange this formula that I have. And now we can define, or we can get more into detail about what this guy is. Distance travel for every unit of time, distance travel per second. If the distance travel from the start is equal to distance per second into total time, I can rearrange this formula and say, in a simple way, distance is equal to speed into time. This distance travel per second, we can now give it a formal name. The formal name that we choose to give it is speed, and that makes sense, right? Because speed means how fast is something going, right? And distance travel for every unit of time is a good measure of that. How much distance is travel per second? That's a good measure of how fast the car is going. Hence this distance per second, we call it speed. Time elapsed is here. Total distance traveled is here. So we get a simple formula here. The same thing written in a cleaner way. Distance is equal to speed into the time elapsed. Going a little bit further, we can now rearrange this formula and show it in a different way as, if I want to know the speed, speed is simply the total distance covered divided by the time elapsed. Move the time elapsed from the RHS, the right hand side, to the left hand side. Speed is now equal to the total distance covered by the time elapsed. And you can make that calculation in a bunch of different ways, right? You can say, well, it travels 5 meters in 1 second, right? So 5 meter divided by 1 second is 5 meter per second. If you don't want to use this part of the calculation, you can use a larger interval where it travels 10 meters in a total time of 2 seconds. So how much distance will be traveled in 1 second? Well, 10 meter divided by the 2 seconds will again give you 5 meters for every second, right? You can continue. You can see where I'm going with this. You can take 15 meters divided by 3 seconds, right? 15 meters by 3 will still basically give you in the simplest form 5 meters for every second. So you can make this calculation in any way. Take whatever distance, take the corresponding amount of time, divide the distance by time, and you will find out how much distance is traveled per unit time, which is what we refer to as speed, the unit obviously being meter per second. Another way of thinking of the same formula is back to our supermarket pen analogy, right? The speed is basically like the price per pen, right? The price per pen, how do we get in a shop? We will find out the total money I paid. If I know the total amount of money that I paid and I divide that amount by the number of pens I bought, then the total amount of money is shared across those number of pens. So if I divide the total amount of money by the number of pens, I will get the price per pen. That's the same thing we're doing here. Divide the total distance traveled by the total time that has elapsed. Then you will find out how much distance is traveled per unit time, which is therefore what we call as the speed. Continuing with our exercise of using mathematics to simplify our life, now we go back to this formula, distance is equal to speed into time. Now we know where this formula came from or where this relationship came from. If you don't want to use the word formula, it's basically a relationship, right? Now, just to make things a little bit more succinct, the distance traveled from the start, I can refer to it as, or I can use a simple letter to represent it, any letter in the alphabet that you want. Let's use the letter Y. So the distance traveled from the start, we use the letter Y, is equal to, that is the same as the speed, how much distance is traveled per unit time. In this experiment, in this case, we know that the speed is constant. Cruise control, 5 meters per second. So the speed is 5 into the total time elapsed from the start. Now, total time elapsed from the start, I know that we've used the letter T for time, but because we are setting ourselves up for the entire mathematics course, usually when we have an unknown quantity or a varying quantity, we use letters like X and Y. That's why I'm trying to just fit it into that kind of framework. You can use whatever letter you want, it's fine. For now, we will refer to the time elapsed as X, how much ever time elapsed, 1 second, 2 seconds, 3 seconds, whatever, we'll call it X amount of seconds, Y amount of meters. Speed, of course, in this experiment is constant, 5 meters per second. Hence, this distance equal to speed into time now becomes Y is equal to 5 into X. Simpler way of writing 5 into X is Y is the same as, or Y is equal to 5X. This is finally a much simpler way of telling this whole long story, right? The whole long story, which I end up anyway making longer because I tend to ramble on. Instead of all of that, Y equal to 5X. You can imagine how useful math is for someone like me, the rambler, right? So Y equal to 5X. What is the speciality about this deal here? Basically, in the simplest form, this is in the format something on the left hand side is equal to or is the same as something on the right hand side. Y is equal to 5X. I can get Y by doing the calculation 5X. This is basically what we call an equation. Equation means something equal to, something the same as something else. In this case, it's Y equal to 5X. This is the simplest form of an equation. Now, as I said earlier, we're learning about the tools. You will start to see in this course, no matter how advanced we go in our mathematical journey, essentially we'll be dealing with different kinds of equations, right? Some more complex than the others, but essentially all derive from real life in the same way. So if we get this is the template that we can use to understand and break down everything else by relating it back to day-to-day real life, because all this is real stuff. It's not some abstract language you learn in some book, right? So if you connect it to real life, every single equation that we will learn later on, if you connect it to real life, you will essentially see that there's a clear link, and then there will not be any doubt in your head as to what you're doing and how to do it. So now we have a simple equation, Y equal to 5X. So why do we need these equations? A couple of very important uses of these things that we now call equations. The first thing, and this is just a fancier way of saying what we just did, what do we say so far? Y equal to 5X is basically the simplest and clearest way of telling a very long story, right? So this in mathematics we refer to as a mathematical model, right? Something is happening in real life. Now we use the language of mathematics to make some sort of model, some sort of a mathematical story to tell the real life story in a simple and clear way. This is extremely useful. Again, something we use in greater dimensions as we go along, but essentially the same idea, converting something in real life to something clear and succinct in the language of mathematics. We call it a mathematical model. This equation is the simplest, most basic form of mathematical models that we will encounter as we go along. That's the first important use of mathematics and of equations. Now, a mathematical model like our equation is not just useful for summarizing the story. It can also now be used to help us make predictions for a much later stage in this experiment, something that we refer to as extrapolation. That means what may happen much later. Let's take the example of extrapolation. If everything in this experiment is going in the same way, now our equation, our mathematical model y equal to 5x will help us make a prediction for any time later in the future. So you can answer a question like this: what will be y when x is equal to 500 seconds from the start? Which means after 500 seconds have elapsed from our start point, which was t equal to 0 seconds, when the car was at the start position, car keeps going, and 500 seconds have elapsed now. After 500 seconds, how far is the car away from the start position? What is y when x is equal to 500? If everything stays the same, if the speed doesn't change, we can use this equation. Y is equal to 5x, which is y is equal to 5 meter per second into how many seconds? 500 such seconds. Every second 5 meters. Hence we can easily get the answer as the car will be 2500 meter away from the start, of course in this direction. So this simple mathematical model can now predict for any time in the future, right? And we can also work it back for a time before the experiment started that we'll see in later applications. So the predictive value of equations makes them absolutely wonderful tools for us. Another kind of prediction that we can make using our equation, using our mathematical model, is the other way around. In this case, our question is phrased differently. Now we want to know what is x when y is equal to 1000 meter from the start. So now in this situation, again we're extrapolating. We want to know something way in the future, but the information that we have, what we are starting with, is not the time. That's actually unknown for us in this situation. We want to know, okay, the car keeps going. At some stage, after a certain amount of time from the start, the car will be 1000 meters away from the start. So when the car was 1000 meters away from the start, when it reaches there, how much time has elapsed from the start? So we want to know x given y. Again, we can use the same mathematical model, the same equation, just by moving things around. Y equal to 5x. Now y is known, so 1000 meter total distance travel is equal to 5 meter per second, how much distance per second, into how many ever seconds are elapsed. That is unknown right now. Rearrange the terms, therefore how many seconds that have elapsed will be 1000 meter, that is y, divided by the 5 meter per second speed. So 1000 meter divided by 5 meter per second, that will essentially tell us that 200 seconds have passed from the start, and that is when the car reaches the position 1000 meter from the start. So this is another way in which our equation has a predictive property. Now to finally wind down this first lesson in our exploration of the basic tools is some terminology that again we'll be encountering as we go along in this course, and also as you go along in other science courses like physics and chemistry, biology, etc. Very useful terminology because they have real meanings. Now coming back to our equation, y equal to 5x. Now we're going to give some important terms to each of the characters in our equation. This y, when you use the equation in this form, how does this equation work in this form? We don't start with y. When I write the equation in this form, what do we do? If you look at the first example of our prediction case, we knew a value of x, a certain amount of time elapsed. We put that value of x in this equation. Then x into 5 gave us y, right? So this y, its value, that is the distance traveled, its value depends upon what value you enter for x, what value you enter for the time elapsed. If you enter x as 5 seconds, then you put 5 in this equation, then 5 into 5, 25. 25 meters comes as the value of distance traveled y. If you change x to, as we saw in the earlier example, 500 seconds, 5 into 500, that gives you the value of y, right? So the equation in this form has y depending on the value of x. You can think of x as the input, right? You put in x and y comes as the output. It comes out from this equation, right? Because of that, y in this form is referred to as the dependent variable. Why dependent? Because its value depends on what you plug in for x. Well, that's why we use the word dependent. Why do we use the word variable? Because this distance, right, refers to distance of the car from the start, right? And that's not a fixed distance, right? Because the car is continuously moving. So based on how much time you are interested in from the start, you plug that in and you get different values of this distance, right? So it's not a constant, it's not a fixed number. Anything that's not a fixed number in mathematics, we don't know what the number is until we do a calculation, right? So until we know what the number is, we will give it a letter, which is basically what we refer to as algebra, right? And therefore, until we get a particular case, this distance can keep varying based on the amount of time. Hence, we use the term variable, something that keeps on varying or keeps on changing as the experiment proceeds. So this is why y is called the dependent variable. It varies and it depends upon what you plug in for time elapsed or x. By the same token, what about our friend x? Again, in this form, when I'm using the equation in this form, I always start with x, right? I say how much time, okay, after 10 seconds where he is, after 500 seconds where is the car, right? So I know what my value of x is. I start from there, right? So in this form, the time or x is not really dependent on anything else. It's something that you plug in. It's like, okay, it depends on what you want to know, right? So this x really doesn't depend on anything else in this equation when the equation is in this form. It's what you start with and you put in based on what information you want to know, right? How much time you want to know after 10 seconds or 20 seconds or whatever. You take the value that you want and you plug in and then you find the value of distance. So in this situation, x will function as the independent variable. Independent because you are starting with it, right? So you fix it to whatever you want and then you use that to find out after how much time, where will it be. So it's something that you start with. And again, you use the term variable. Why? Because you can take any value of time that you're interested in, right? You can find out, okay, after 1 second, I'll plug in x equal to 1. If I want to know after 100 seconds, I'll plug in x equal to 100. So its value also can keep changing based on where you want, based on what question you are asking. If I want to find out where the car is after this much time, or if I want to find out where the car is after much longer time. So based on that, you put it in, right? So therefore, its value keeps varying. So we use the term independent because you start with it, variable because it can be anything that you want, right? For what you are looking for. So independent variable. And the last term in the equation in this case is the speed of the car, right? And in this experiment, we have kept the speed fixed, constant, which means throughout the experiment, no matter what time you are searching for, no matter what distance you are looking for, the car is still going in cruise control. So its speed is held constant. Constant meaning here we know the value, right? So many times if we know the value, it basically becomes a number. I don't need a letter to represent speed in this situation because I already know that no matter what, the speed doesn't change from 5, right? So two things. In this particular experiment, the speed is a constant. Not just that, in this case, we also know what the value of that constant is. And therefore, we don't need to specify it with a letter. We can specify it with a number because everything about it is completely known. Another way of describing that term in an experiment which is held constant, which is held fixed, is to use the term controlled variable. Now I know it feels like a bit of an oxymoron, no? You held it constant, why the hell are you calling it variable? We're establishing some terminology which we will be using in general for all cases, right? So the best way to think about it this way is, in this experiment, the speed is held fixed, the speed is held constant, or it is held controlled, right? Why do I still call it controlled variable? Is because I can do another experiment where the car has a different speed. In that experiment also I can keep it fixed, but instead of keeping it fixed at 5 meter per second, I can keep it fixed at 100 meter per second. I can keep it fixed at 200 meter per second, right? So you can vary the speed and put it at different values and run the same experiment again, but for that experiment, whatever value you chose for speed, you hold it firm, you control it, right? So technically you can still think of it as a variable, but a variable that you carefully control. In this case, we keep it fixed, constant at 5 meter per second. So 3 basic types of variables that you will see in all mathematical models, all equations. The dependent variable, sometimes called the output. The independent variable, what goes in, sometimes we call it the input. And when we are trying to find out the relationship between the two, the dependent and the independent, what happens for y when x is this much, what happens for y when x is something else, as we are trying to find that out, anything else that's relevant, we'll keep it constant, or we'll keep it fixed, or we'll keep it controlled. The third type of variable is a controlled variable. So once we get a handle on this, connecting this to our real life example, you can use this as a guide. All other situations in mathematics, no matter how complex they will just be variations of this. Variations on a theme, as we like to say. That's about it basically. Now we have a clear idea of the potency, the power, and the beauty, and the simplicity actually of mathematics. Now we've introduced our first important tool, mathematical models or equations. Now, if you've heard the saying, a picture is worth 1,000 words, and by God we need it, because I've said much more than 1,000 words today, right? So now that we have an equation, the next thing is, well, this is great, this gives me a lot, but can I say the same story? Can I tell the same story in an even simpler way, in an even clearer way, using pictures? Because 1,000 words or more can be replaced by a single picture, which will actually convey pretty much all the same information. So our next lesson, our next toolkit item, our next tool will basically be trying to figure out if we can take a picture of this equation, if we can draw a painting of this equation, wherein by looking at that picture, by looking at that painting, I can get all the information that I got by solving the equation here using simple algebra. Can I do the same things by looking at that picture? So what is this picture of an equation? That will be in our next class. Namaskaram.